Hello and welcome to... Wait, what do you mean you can't see me? Oh, hang on. I see the problem. One sec. Oh, hey there. My name is Rob, and you're probably here for animation secrets from CAD Model of the Day, right? Well, I won't waste any more time, so I'll meet you on the slide deck. Okay, so gags aside, a quick word on who the presentation is for. Obviously, I love that you're here watching right now, but I also respect your time and want to help you make an informed decision. Basically, if you're at least tangentially familiar with making animations in SOLIDWORKS, you should be good. I will be going over some basics, but just enough to contextualize the special techniques we'll be focusing on. But if you never made an animation before, the things I go over may be difficult to follow. If that's the case, you should check out Bringing Animation to Your Assemblies, How to Animate in SOLIDWORKS by Anthony Sandri. Looks like he's made a fantastic presentation for people who have never even heard of animating in SOLIDWORKS. So at this point, you may be wondering who I even am. Well, I'm a nerd, that's what. But more specifically, I currently work for SJK Energy Systems doing general CAD work. I've been using SOLIDWORKS since 2015, where a year later I became a certified SOLIDWORKS expert and then started my YouTube channel. A year after that, I graduated from Case Western Reserve University and start working for DesignPoint, a SOLIDWORKS reseller. A year after that, I become an elite applications engineer with 26 SOLIDWORKS certifications. And since then, I started working at my new job and then started CAD Model of the Day in 2019. For those of you who haven't heard, yes, I am the lunatic that is modeling and posting a CAD model every single day until the heat death of the universe. And yes, it is still ongoing. Today, February 10th, 2021, is day number 461. I haven't done it yet, so if you have any suggestions for what I should model, let me know in the chat or in the comments. The models in this presentation come from the CAD Model of the Day project, but it's just the tip of the iceberg when it comes to what I've modeled thus far. If you want to see the rest of them, follow me on Instagram and Twitter at VirtualFlatCAD, subscribe at YouTube, VirtualFlatCAD, where I occasionally host live streams of me doing Model of the Day. Join my Discord. I'm all about that community, and I got one going on my community Discord. And for all else, see linktree/virtualflat for an exhaustive list of my other social media stuffs, including my LinkedIn. But without further ado, let's get into it. So, if you've played around with SOLIDWORKS animations or just came from Anthony's presentation, then you'll know that there are 3 modes you can select from when creating a motion study. There are the plain old animation, basic motion, or motion analysis. But for all intents and purposes, we can split these up into just 2 different paths. And my decision-making process I'll show you today will have to do with selecting one or the other. The main question is, do we know how all bodies will move or not? If we do know, then we can use the animation mode. Here I'm calling it a simple animation to distinguish it from other modes, but as we'll see soon, you can get some very brilliant animations using this mode. From there, if we need the help of physics to determine how some bodies will move, then we will either use basic motion or motion analysis. And that will be based on the level of SOLIDWORKS you have access to. If you have SOLIDWORKS Premium, I always recommend using motion analysis over basic motion. But if you have standard or professional, you can use basic motion. Simple animation or motion analysis? That is the question. That is definitely oversimplifying it, so let's take a look at this table to compare more aspects. Now, this list isn't exhaustive, but it does highlight the main differences between the modes. Another way to ask the question is, can we get the motion we want from keys, motors, or mates? Or do we need gravity, solid body contact, or springs to get it done? You may notice the rebuildable parts down at the bottom, and I'll circle back to that later. But for now, let's play a game. I'm going to show you some examples from the CAD Model of the Day project, and you try and guess, based on what I've told you, is it a simple animation or a motion analysis? Let's go. Alright, so this one was one of the first animations I ever posted to the Model of the Day project. This is from the 507 Mechanical Movements book, a book of mechanisms compiled by Henry Brown in the 1800s. They make excellent animation exercises, by the way. Check it out. But this one here is movement 27, where the black followers imparts its motion on the gray tracked wheel. So which did I use? A simple animation or a motion analysis? Truth be told, you can actually use either or for this one, but I chose to use a simple animation. Why? Well, in general, a simple animation will rebuild faster than a motion analysis that has to compute contacts, forces, accelerations, etc. Taking a closer look at the assembly file, we see that it can actually get the motion I need just by using mates. If you refer back to the table we were looking at earlier, we see that any animation mode can solve mates. So the takeaway here is this. If you can mate your assembly such that you can get the desired movement just by clicking and dragging, then just use a simple animation and add a motor to drive the member you would normally click and drag. That one was pretty straightforward, so let's take a look at this next one. Here we have two spur gears, but you may notice they look a little funky. I would like these gears to always be in mesh. Based on what I told you from the previous exercise, some of you may be thinking, wait a minute, doesn't SOLIDWORKS have a gear mate? If we can get that mate to solve the meshing, then we could just use a simple animation for this one too. It's a good thought, but that leads me to my next takeaway. Mates are just math. They don't care what your part looks like so long as they satisfy the mate's requirements to solve. Case in point. Here's an assembly with two regular spur gears mated together with a gear mate. I can suppress the feature that creates the teeth and you'll see the gear mate still functions. I can even move them apart and still the gear mate does not fail. It doesn't care what the teeth look like or even if the gear has teeth. Somewhere in SOLIDWORKS there is a line of code that says when this thing turns X times, this other thing turns Y times in the opposite direction. The rotational speed is directly tied with each other depending on the gear ratio. This won't work for movement 38 over here because the gear ratio changes depending on which part of the gear is in mesh. What we need SOLIDWORKS to do is to take into consideration the shape of the tooth and actually compute solid body contact. We need to use motion analysis. Once we know what to do, executing this is straightforward. Make sure they're mated onto their shafts and they cannot slide along their shafts. The only degree of freedom they should have is one rotational degree of freedom each. Mesh them manually, then go into motion study. Remember to set the type to motion analysis, then add the contact and select the two bodies. Add a constant speed motor and calculate. And there you go. That's two down. Here's an animation from a recent CAD model of the day. It's from day number 418 and it's a piece of DuPont wire stretching across a breadboard. Now, as anyone who has used these wires will tell you, they don't do that, but that's okay because I'm simply exercising my artistic liberties. Now, circling back to the table I showed, it's now time to talk about the rebuildable parts row down there. What do I mean by that? Well, a quirk of the simple animation mode is that it performs a full rebuild every single frame. Yes, the thing that you hit when you want SOLIDWORKS to recalculate a model with a new dimension happens on every single frame on a simple animation. But what does that have to do with our DuPont wire? We need to recall another function of SOLIDWORKS assembly modeling. We can actually construct part features based on the size and position of other parts in a shared assembly. This is called top-down assembly modeling if you want to know more about it. But the real question is this. Let's say I draw a spline and say that one end is coincident to a vertex of a part, and then say the other end is coincident to a vertex of a different part. If I move those parts away from each other in an animation, does the spline get longer? The answer is yes, so long as the assembly is rebuilding to reflect those changes. And that last part is super important. And you might be wondering, why is that? Well, assemblies do not rebuild in basic motion or motion analysis, at least as far as I know. I suspect that since SOLIDWORKS is calculating forces, accelerations, and body contact, it may be too much to also change the shape of the parts while all of that is going on. Another takeaway is this. If you need a part to change shape in the middle of an animation, we must use simple animation. Motion analysis will not work. So knowing that, we use a simple animation for this one too. Going into the assembly, the DuPont wire is actually modeled as two ends and another part file contains the wire portion. The spline that represents the wire has a coincident relationship to the top center of the wire end, and the other end also has a coincident relation to the top of the other wire end. We can now go into motion study, make sure animation is selected from the drop-down, and move the ends around in the assembly however we like. I use mates and key points for this one, but you could just as well use the linear motor if you wanted. And that's basically it for this one. Now this one is one of my favorite animations. If you've played Crash Bandicoot before, you've definitely seen this bounce crate. Our hero hops on it and it sends him careening upwards with a satisfying bounce. This is what I wanted to create in SOLIDWORKS, which I remind you is an engineering program. But I like challenges, so I did it anyway. Just so you know, this exercise will feature pretty advanced modeling and surfacing. If that's not your cup of tea, I get it. There's more afterwards. In the meantime, visit my Instagram page at VirtualFlatCAD and tell me what your favorite model of the day is thus far. And follow. I do special things like giveaways for milestones like day 500. I'd love to see you there. So anyway, this crate is changing shape during the animation, so this must be a simple animation. The interesting bit is how I modeled basically a cube that squishes and stretches during rebuilds. A normal person would model a cube by sketching a square and extruding it. That won't work for us since that's how you get a rigid cube. We want one that flexes. The way I did it, I accomplished it with surfaces, basically modeling each of the 6 faces at a time. Now that we're here in the part file, I'll sketch on the front plane and give it a line starting at the origin going straight up. This line will be 24 inches, and this will be the default height of our box. This is what I like to call our controller line. It sets the current height of the box, and in the end, we're going to be stretching this line in order to make the animation work, just like the spline of the DuPont wire. In order to start with our squishy cube, I'll do a new sketch on the top plane, and I'll get a square to go over here. Sketch that, make those equal, and set this to be 24, just like the controller line. And with this, we'll go to the planar surface command, and that's our bottom face. The top face needs some consideration. In the animation, the top face moves up and down, so we need to set that up here. Recall that our controller line sets the height of the box. So what I'll do is get a plane, click the line and its endpoint, and that will put a plane right on the end of that line. And then on this plane, we'll go a sketch and yet another square, just centered about the origin, just like the other one. See if we can get that in there. Looks like I missed, so I put that equal and 24. And this will be friends with the planar surface command too. And there we go. We have a top and a bottom plane. So far, so good. I recommend to test often. So what I'll do is I'll go into our controller line sketch, and what I might even do, controller line. There we go. Now we know what it is. Controller line. Click on the dimension and set it to driven, like this. And go to features and make sure that Instant 3D is on. If Instant 3D is on, that means I can actually grab a free end of the line and just drag it up and down, and it'll automatically rebuild. And what we should be seeing here is, well, exactly what we're seeing. The top plane, the top face, excuse me, should be right on the top of that line at all cases. And looks like this is fantastic. So let me put this one back. You were 24. We'll do that. For the sides, I know I can use rotational symmetry to pattern 4 faces to make the box, so we don't have that much work ahead of us, but we do have some setup to do before we can get the side surface in there. I am going to create what I like to call a sketch mechanism. It's not sketches of mechanisms, it's more like the sketch itself being the mechanism that moves stuff around in a SOLIDWORKS part file. The goal of this sketch mechanism is to represent the bloating and stretching of the side as the crate deforms. This may be hard to see until it's done, so bear with me for a moment. I will need a new sketch on the front plane. And let's get that centered up. Fantastic. And let's get a line. And I'd like a center line, so I can actually hit Alt-C to turn that into a center line. And I'll start with this horizontal line, this endpoint, and our controller line can have a midpoint relation. And the line itself and the controller line will share the same length with an equal relation. And this is what relates our sketch to our controller line. If we didn't do this, the sketch wouldn't update when we move that controller line around. Next, we'll draw yet another line off to the side, another center line. Get this end and merge it to this line here. And I'll give this line a length of 36 inches. The reason being, I need the very end of this line to be right underneath the edge of our planar surfaces, both of them. And we'll see what that does for us in a moment. But the next step here is we'll get a line, and I'll get a regular line this time. It doesn't really matter because we're not going to create any features with this, but it helps differentiate, what the important lines will be when we select them later. But the end of this line will be pierced to this, and the other end of this line will merge right into this one right here. It's important to realize that make sure that there's no vertical here. If there's a vertical relation, it won't throw an error at first, but when we try and move this sketch around, it'll throw an error. We don't see that here, so we know we're good to go. And the last thing we gotta do is just rinse and repeat for the other side, so I can put the merge just like that, and put the pierce like that. And that's about it. 4 lines. So let's see what this does for us. If I run a test here, grab this and say make driven so the end is loose. As you can see, if I stretch this line longer, it pulls in that 36-inch line, and those 2 lines follow it, which is why it was important that it couldn't be vertical. And the opposite, if I make it shorter, it'll shove that 36-inch line out and create this new angle. So that is our sketch mechanism. You could see that mimics the buckling and the bulging behaviors that I need from my box. All right, before I continue here, let's put the line back to how it was. So you're no longer driven and you'll be 24 inches. So it'll look just like that again. Okay, the next step, we need to create a boundary surface between this edge and this edge. But here's a kicker. For the direction vector, I'll select this line, so that is putting its tangent influence into that. I'll select that line for there, select direction vector again, and then select this bottom line, meaning that this boundary surface should follow those 2 lines. So you may see where I'm going with this. So let's do yet another test. Let's get in here, driven. All right, let's try it out. So if I pull this line up, you see the surface buckles inwards because it is following the direction of our lines here. And if we shove it downwards, maybe a little more, there you can see it's being shoved outwards. This is perfect. This is exactly what I needed from my sketch here. Now, before we get ahead of ourselves, there still remains the problem that we don't have a box yet, and it should be solid at that. So for the rest of the faces, a circular pattern around this line should do just the trick. So let's go do that. Circular pattern, this line, set it to bodies, and give it this guy. There we go. We have our cube. Now there remains the issue of turning this cube into a solid. The fastest way to do that is to use the intersect command. Basically, if you have a collection of surfaces that completely encloses a volume, just like you see here, or in other words, it's airtight, the command will be able to turn that collection of surfaces into a solid. Sounds perfect, but we have to make sure that the airtight condition is met throughout our animation. So let's do a little bit more testing here. Let's go back into this, set to driven, you know the drill. And let's stretch our line upwards so you can see that there is a lot of overlap, which is why I don't want to use knit. For knit, you need to have like perfectly conjoining edges. But this will work perfectly with the intersect command. But if I stretch this line downwards, we have a problem here because when this surfaces buckle outwards, it actually causes an opening. So we need to fix it, but thankfully it's nothing too complicated. I'll just roll back, go to my surfaces, and say extend surface. We just need to extend these 2 edges outward, and you see when I circular pattern, hey, no more hole. This is perfect. All right, and all we have to do now, I believe, is just to give that to the intersect command. So we'll go over here, select all of our surfaces, see if I can do it from here. That'd be nice. Say create internal regions, intersect, and there's our cube. Well, it's a little squished right now. And we'll hit OK. I'll do a bit of cleanup work here and just say delete keep body, just keep this. And there's our cube. So let's continue our testing. Wow, I basically just snapped it to 24. That was kind of lucky. But if I pull this up even further, you know, that's awesome. You know, this has been one of my favorite projects. So this might actually be the most complicated cube to ever exist in SOLIDWORKS. Who says prismatic modeling isn't fun? The rest of the stuff on the crate are just details and is beyond the scope of this presentation, but let's animate this cube how it is. So to get this set up, let me put the controller line back to 24. Like this. There we go. We can just save it as is. And let's begin a new assembly. Now for this assembly bit, we'll just take our part here, place it right down on the origin, and now we need something to articulate this line, like a dummy part. Something like, I don't know, a cube. Oh god, anything but that. Oh, just kidding. It just can be a regular cube this time, and actually I have one pre-prepared. So let me just get the dummy part, and I'll just place it out here in space. To get it in place, I'll mate the front planes together, and the right planes can come together as well, just like that. And now we just have to save this assembly, because now what we're about to do is edit component. Well, I gotta select this one, edit component. There we go. And select our controller line, get into the sketch, and set that to driven. That'll make this end free again. But this end is going to be friends with this face, with a coincident. So we can get out of that, exit the component, and it's looking pretty good. So let's test. We push this down and say rebuild. Yeah, that's working perfectly here. So all we got to do now is go into a motion study, and let's get a linear motor. I'll do an oscillating like that, maybe going the other way, and I'll just put in some numbers. These things are pretty fun to play with, so let's do that, and let's just calculate, see how that goes. Pretty cool. This looks like this works perfectly. And one last thing, it's kind of weird to have a little cube sitting on that, so all we have to do is just right click on dummy and say hide. And that's it. There it is. Was it worth it? I don't know. But was it fun modeling? You bet it was. So with that, let's get on to the next one. So what do we think? We see a gear in the shape of an ellipse meshed with a circular gear. I would like to spin this arm around at a constant rate and have the circular gear mesh with the elliptical one. Because of the shape of the gears, we would expect the circular gear to spin at a non-constant rate, right? So we have to use a motion analysis, right? But then look at this spring. Isn't that rebuilding constantly? That would mean we have to use a simple animation, right? Are we just stuck? How did I animate this if the two functionalities I need are mutually exclusive to each other? Do I use both modes? Well, yes. Now, before you go type in the chat, Rob, you dingbat, you can only select one option at a time from the dropdown. This will never work. Hear me out. Recall this overview slide here. We can use a simple animation if we know how all bodies will move. Right now, we don't know how exactly this circular gear will move. We know that it's a speed that's changing, but we don't know the exact numbers, so no dice, right? But let's consider the table again. We need both of these, right? So let's start with a motion analysis with solid body contact. Use the kinematic analysis functionality of motion analysis to get the exact speed data of the circular gear. Then we feed that data into a simple animation into a motor. And then we'll have access to rebuildable parts. And that, my friends, is the game plan. Let's see how it's done in practice. Here we have the assembly with the correct amount of mates. As you can see, when I move the assembly and hit rebuild, the location and size of the spring updates. All we need to do now is to start a motion analysis. Specify a constant speed motor to the arm and contact between the two gears and let it run. As you can see, the gears mesh perfectly, but it leaves the spring behind. It never rebuilds, so the spring never realizes that it needs to move. If it wasn't for that spring, it would be done. But now that we have the motion of the gears, we can move on to the next step, finding and extracting the data from the circular gear. We specify a new plot, select distance, velocity, acceleration, then angular velocity, and then select the axis it's rotating about. In my case, it's about z. And then something stationary for the measurement to be taken against. We get a plot of how the speed of the circular gear ebbs and flows as it travels around. Now that we have this data, how do we get it into another motion study without manually entering these numbers? If we right-click on the plot, we have the option to export the data as CSV. We do that and then create a new motion study, this time leaving it on simple animation. We create the constant speed motor just like the other one, then we create a new motor and this time go to data points, and there you'll notice there is a button for importing data. You guessed it, click it and select the CSV file we previously exported. As you can see, it does all the work for us in terms of data entry. Accept the motor, recalculate, and there it is. Yet another challenge knocked down. Okay, I gotta be honest. For this last one, we're about to make SOLIDWORKS do things it was not designed to do. For this next segment, parental discretion is advised. No, grand parental discretion is advised. If you are under the age of 65, please leave the room now. We are going to animate rope in SOLIDWORKS. Now, before you go to the comment box, yes, I do know about the belt and chain feature for assemblies. This is not that. Belt and chain is designed to work with a constant cross-section belt or the discrete linkages of a chain. We need a strand of rope of constantly changing cross-section to move along a path. Are you ready? So, I gotta be honest with you, I really wanted to do the step-by-step on this one, but it's just too much. And so in the interest of time, I'm gonna tell the abridged story. This is my biggest secret. So, this thing here that is stuttering very nicely, the thing that's kinda acting a little bit like rope, but not really, and looks like really thin phone wire, that, I got to that point pretty quickly. But I was stuck here for a while because I could make a sweep that kind of acts like a rope, but I just couldn't make it look like a rope. Like I couldn't find a feature that can look like rope and rebuild. So let me first show you how I got to this point real quick, and then I'll show you the problem. So let me stop this, and once that stops, can go into the belt part. So I actually did use belt and chain for the initial feature here. But if you look here, so this is the sketch as was given to me by the belt and chain. This tiny line is a little bit less than half the width of my rope, or the intended width. I swept a surface along this path. Just like this, you can specify twisting along a path. So this little line is going along this path and it's just twisting as it goes there. And if you convert that into a 3D sketch, you can actually use it for sweeps. But here comes the problem. So let me hide that away. Sweeps are extremely computationally expensive, which is why I was why I was stuttering so bad. And it took forever to rebuild for this example. But if we edit this feature, if I try and make this look like rope, or try to, so you can see it's really thin right now, I'd like it to be a lot thicker, but you know, half an inch is what I wanted. But if I do that, it's probably going to spin for a while, so I'll see you in a bit. Oh, here we go. So it's trying to do something. That's not a rope, sir. And if I hit OK, it probably will yell at me. Sweep could not be completed because it's self-intersecting. I was stuck here for so long. And the problem is, like, I couldn't find anything to use as a rope that wouldn't self-intersect. And then I realized there is a kind of body that doesn't check for self-intersections, and that is graphics bodies. But the problem is, usually graphics bodies you import just to kind of look at and, you know, sketch from. There's really no features in SOLIDWORKS that create native graphics bodies. Almost. So let me introduce you to my friend WeldBead. If I go to Weldments, zoom into this. Oh, actually, I just need to roll down. So if you do a weld bead, switch to weld path, you can actually have this sweep along a path, and it does this caterpillar graphics things that there you can see there's the self intersections, but since a weld bead is graphics, it doesn't care. So we do that and we suppress the sweep so it actually perform better. Okay, so really quickly before I recalculate this, how it even gets its motion, I'll say a word on that. So remember the little line I pointed out to you earlier? Well, similar to the Crash Bandicoot crate, instead of stretching this line with a dummy part, I actually rotate this in place. So the sweep is actually rotating, so it's the exact same thing as like the barber shop pole illusion where it spins in place but it looks like it's advancing. So that's how that is done. Go back and hit recalculate. I'll see you in a sec. And there it is, moving rope. It is super glitchy, does not work very well, doesn't like colors very much, but it's there. And maybe it's a reason for the SOLIDWORKS dev team to add graphics bodies. Who knows? It just goes to show what a deep understanding of SOLIDWORKS can do for your particular specialty. I can't weld. My welds look like the T-1000 had a cold and sneezed on a bar of metal. But I wouldn't have been able to accomplish that if I didn't understand the Weldments functionality. That's why it's great that you're here at 3D Experience World. This is the perfect place to learn this kind of stuff, and I hope you'll stick around for more presentations. Stay awesome, and I hope to see you on my channel for more content. Thanks for watching.